Hello, my name is Mildred Verlage, and welcome to another lecture from the 2020 Honors Chemistry Short Lecture Series. Technology has become a valuable part to our daily lives and to society. We basically rely on our cell phones and laptops for everything. More importantly, we rely on wireless technology that we can take with us everywhere we go with no problem, and we just have to charge every few hours. This is thanks to the lithium-ion batteries. Though, what happens to the lithium-ion batteries in your device when you get a new device or you run out of battery? Well, in today's lecture, I will discuss the recycling of lithium-ion batteries. Inspired by my CEN article, It's Time to Get Serious About Recycling Lithium-Ion Batteries. The title of this lecture is Recycling Lithium-Ion Batteries. We are going to be discussing the inspiring CEN article, history, main components of the battery, recycling lithium-ion batteries, comparison, recycling process, what is being done today, battery identification, benefits of recycling and the dangers of not doing so, conclusion, and we're excited. My inspiring CEN article was It's Time to Get Serious About Recycling Lithium-Ion Batteries by Mitch, Jacoby. This article acknowledges that lithium-ion batteries have made portable electronics like phones and laptops ubiquitous and are doing the same for electric vehicles. It covers how much lithium-ion batteries are being consumed in different countries and their recycling percentages. Today, in the European Union and in the US, less than 5% of these batteries are being recycled. The article explains the process that these batteries undergo to be recycled and the different benefits and challenges to recycling these batteries. Lastly, this article discusses new methods to improve the recycling of the lithium-ion batteries that are being created and tested by different companies. A brief history. In 1780, Italian scientist Alessandro Volta invented the first battery in an experiment that was inspired by his fellow scientist Luigi Galvani. In Volta's honor for his discovery, the standard unit of electricity was named the volt. In 1912, G. and Lewis began experimenting with lithium batteries. The foundation of the lithium-ion battery was established by M. Stanley Whittingham during the oil crisis within the 1970s. In 1985, Akira Yoshino created the first commercially viable lithium-ion battery, with John B. Goodenough's cathode as a basis. The lithium-ion battery was then first sold by Sony and entered the market in 1991, and recently, in 2019, the Nobel Prize in Chemistry was awarded to John B. Goodenough, M. Stanley Whittingham, and Akira Yoshino for their development of the lithium-ion battery that revolutionized the world. The main components of the battery. A battery is a device that stores chemical energy and converts it to electricity, which is known as electrochemistry. The system that is the base of a battery is called an electrochemical cell, and a battery can be made up of one or several electrochemical cells. The main components of the battery system include two electrodes, the anode, which is negative, and the cathode, which is positive, and an electrolyte, which includes a separator. Recycling lithium-ion batteries. Since lithium-ion batteries are complex products, there are different possible paths for their recycling. The three processes for recycling include pyrometallurgy, which is smelting, hydrometallurgy, which is leaching, and direct or mechanical, which is physical. Depending on factors such as quantity and characteristics of the material available, and factors like quantity and value of the materials that can be recovered, process components can be combined in different ways. Now, pyrometallurgy extracts the metals by thermal treatment, while hydrometallurgy involves aqueous processes, and mechanical or direct involves crushing the battery cells. A comparison between the three processes. In contrast to pyrometallurgical processing, both hydrometallurgical processing and direct recycling are low temperature and low energy processes and do not require large scale. Detailed unit process analysis shows that direct recycling and hydrometallurgy are quite similar processes. However, the key difference between both process streams is the presence or absence of acid in the material. Direct recycling retains the cathode crystal morphology, while hydrometallurgical uses strong acid to dissolve the cathode into its constituent ions, which are sent to aqueous solutions. The main advantage of pyrometallurgy is its ability to handle batteries of mixed cathode compositions. However, the elements must eventually be separated out by leaching before reuse. The recycling process. The recycling process of lithium-ion batteries usually begins with deactivation, implicating a full discharge to extract the stored energy and prevent an unexpected thermal event. Then, the combustible materials such as plastics and insulation are removed with a gas-fired thermal oxidizer, which leaves the battery clean and the naked cells with its metal content. Once disassembled, sorting separates copper foil, aluminum foil, separator, and the coating materials. Pyrometallurgical recycling uses high temperatures to facilitate the oxidation and reduction reactions, and recovers valuable transition metals like cobalt and nickel, but leaves both the lithium and the aluminum in the slag, which makes them difficult to recover. The slag phase is dealt with by the hydrometallurgical process to recover the lithium. This process is also used to recover other valuable metals that may be used to recreate a new cathode. These metals can be obtained by leaching, solvent extraction, crystallization, and precipitation from a liquid solution. Lithium is recovered by leaching and precipitation. The metals that were separated by hydrometallurgy are used to make new cathode material. Direct recycling separates the different components of the black mass, which is active material powder from shredding of cells, by physical processes like gravity separation, which recover separated materials without causing chemical changes, enabling recovery of cathode material that is reusable with minimal treatment. Recovery of anode material using simple physical processes has been demonstrated as part of direct recycling. However, anode material could also be recovered by hydrometallurgical processes. The graphite is regained by filtration, after which lithium carbonate, nickel sulfate, cobalt sulfate, and manganese sulfate are produced. As you can see, here are the possible recycling paths that facilities use when recycling lithium-ion batteries. Though some recycling facilities in different countries may have their own unique steps in the recycling process of the lithium-ion batteries. For example, Umicore, a recycling plant in Belgium, uses a furnace to directly melt the batteries in order to recover 95% of cobalt, nickel, and copper. Afterwards, they use a special gas washing process to clean the toxic incineration products from the fluorine-containing exhaust gases. Another example, Dusenfeld, a recycling plant in Germany, discharges the batteries, crushes them in an inactive atmosphere, evaporates and recondenses the organic solvents of the electrolyte, and separates the electrode coating material from the rest. Battery identification. To utilize the recycling technologies that produce the most valuable products and have the least environmental impact, it is important for the batteries to be identifiable. To identify the different lithium-ion batteries, it is necessary to separate them into streams with similar chemical compositions. The Battery Recycling Committee of the Society of Automotive Engineers developed a label that is placed on electric vehicle battery packs or modules and can even be placed on consumer phones to enable a separation for the different battery types so they can be processed. This label could be read by humans or by machines. This label identifies the battery type, provides additional information about the composition, and supplies information about the manufacturer and the date of manufacture. In addition to facilitating economical recycling, labels can also enhance safety. Benefits of recycling and the dangers of not doing so. This doesn't just apply to recycling lithium-ion batteries, but instead it applies to recycling all types of batteries. A lower dependence on mining for the materials of the battery could restrict the depletion of these raw materials. More natural resources can be conserved, such as minerals and metals. New well-paying jobs and industries would be created in America and in many other countries. There would be a reduction of greenhouse gas emission, which contributes to global climate change. The materials recovered from the recycling process are, for the most part, used to make new batteries, which lowers the cost for manufacturing. Today, those materials account for more than half of the battery's cost. The dangers to the environment. The exact combination and number of chemicals inside a battery vary with the types of battery. However, the list includes cadmium, lead, mercury, nickel, lithium, and electrolytes. When the batteries are thrown away in the household trash, they end up in landfills. Lithium-ion batteries contain flammable and toxic components. Lithium in batteries reacts in a volatile way when exposed, so it can cause landfill fires that can burn underground for years. This releases toxic chemicals into the air, and so the potential for human exposure increases. As the battery casing corrodes, chemicals and metals react with the rainwater that seeps into the landfill and form a toxic soup called leachate, which can percolate into the soil and change its acidity and alkalinity, which can affect the growth of crops and accumulate in the body of crops. The chemicals and metals then make their way into the water supply, eventually reaching the ocean, endangering the aquatic organisms and later harming the wildlife and humans. Dangers to the human health. According to the Agency for Toxic Substances and Disease Registry, cadmium and nickel are known human carcinogens, which is a substance capable of causing cancer. Lead has been associated with birth defects and neurological and developmental damage. Mercury is also highly toxic, especially in vapor form. For this reason, the government banned its use in batteries in 1996. Imperceptible amounts of mercury traceable to other materials used in manufacture of batteries may still occur, though they don't appear as a threat to human health. The accumulation of heavy metals in the human body through the food chain or water sources can have a negative impact on the human nervous system, digestive system, and so on. Some examples. The chemical substances of the cathode material can react with acid and base to produce heavy metals. Heavy metal pollution increases the pH value of the environment. With the anode material chemical substances, the chemical properties of combustion can produce carbon monoxide and so on, and can also cause dust pollution. Carbon monoxide and solid dust particles produced by combustion can pollute the air. With the electrolyte solute chemical substances, strong corrosiveness, toxic gases can be produced when exposed to water or high temperature, which can pollute the air and stimulate the human body through skin and breathing contact. With the electrolyte solvent chemical substances, combustion produces carbon monoxide, and so contamination of alcohol and other organic substances through skin and respiratory contact can cause irritation to the human body. In conclusion, recycling lithium-ion batteries can benefit many countries around the world, as well as help improve the condition of the earth. So far, there are 3 commonly used processes for the recycling of lithium-ion batteries that are used in many recycling facilities across the world. However, different corporations are finding new methods to recycle these batteries to provide and gain more benefits and deplete the dangers that can be exposed to living organisms, the water, and the atmosphere.